For each of the derivatives given below, state what would be the original function. So if my derivative is 2x, what would be the original function? X squared. Very good. If my derivative is 3x squared, what would be the original function?
X cubed.
Yeah, it'd be x cubed. If my derivative is 4x cubed, what would be the original function? X to the fourth. If my derivative is x cubed, what would be the original function? Yeah.
Would it be 1/4 times x to the fourth?
There you go. Yep. And so anytime you do this, you can always double check your answer, right? By imagining what would it look like to take a derivative of this answer. Well, you'd bring down the 4. 4 over 4 is 1. That cancels, and then you get x to the third. So it checks out. The hard part is that, these questions are maybe a little bit more difficult than derivatives. But the good part, the upside for a test like this, is that you can always check your work easily by taking a derivative of your answer and making sure it's the original function. If you don't get the answer right, try again. So what would be the derivative, what would be the original function if my derivative is x squared?
1/3 x cubed.
Mm-hmm. It'd be 1/3 x cubed. Okay. If my derivative is x, what would be the original function?
1/2 x squared.
Yeah, 1/2 x squared. If my derivative is the number 5, what would be my original function? 5x. If my derivative is the number 0, what would be my original function?
Any constant.
Yeah, very good. Any constant. Yeah, if that lowercase c is any number, 5, negative 700, pi, whatever, then that works. You take a derivative of a constant and it's 0. And that actually brings up a really important point that I haven't even remembered until now, which is if I had x squared plus a constant, the derivative would still be 2x. If I had x cubed plus a constant, the derivative would still be 3x squared. If I had x to the fourth plus a constant, or 1/4 x to the fourth plus a constant, those still give you the same derivative. Adding a constant to the end does not change the derivative. So the complete, most generic, general answer to all of these questions involves adding a little constant term to the end. So if my derivative is x to the negative 3 power, what would be my original function?
Negative 1/2 x to the negative 2 power.
Yeah, you're right. So add 1 to the exponent, you get negative 2. And then we're going to divide by that. So whenever I bring down the negative 2, it becomes negative 2 over negative 2, and then the negative 2 becomes a negative 3, and that works out perfect. So you can also write that minus sign in front and say negative 1/2 x to the negative 2 power. Plus c, right? So you can always add a constant and it doesn't mess up my derivative. All right, if my derivative is x to the negative 2 power, what function would give me that derivative? Yep. Negative x to the negative 1 power. What about if my derivative is x to the negative 1 power? What function would give me that derivative?
Negative 1/2, or the.
Last time I taught this class, a bunch of students rushed to tell me that the original function must be, I don't know, something following this pattern, right? So like negative 2, negative 1, maybe like x to the 0 power, right? Maybe it's like a constant, but that doesn't make sense. You know the derivative of a constant is just 0, so that can't work. The answer here is on your common derivatives page. Kyle?
Natural log x?
There you go. Yeah, the derivative of natural log is 1 over x. Yeah. A little bit of a trick question. I mean, I'm not trying to trick anybody, but it doesn't follow the rest of the pattern, you know. It's the one x raised to some power function where the answer isn't x raised to the same power plus 1. When you have 1 over x, the antiderivative is the natural logarithm. And this is what we're doing. It's called antiderivatives. The antiderivative of a function is another function whose derivative is the function we started from. So we're going to use a capital letter to represent the antiderivative. So I'm going to say capital G of x is the antiderivative of lowercase g of x. Oh, sorry. Anyways, another thing you should be aware of is this notation. If you see the tall squiggle means take the antiderivative. And this is kind of like a bookends situation where like you're starting the antiderivative where the tall squiggle is and you're ending the antiderivative where this dx is. So the lowercase d is read with respect to, and I would read this capital F of x is equal to the antiderivative of lowercase f of x with respect to x. Or I could say this question is asking for the antiderivative of cosine of x with respect to x. But the dx tells me kind of where to stop. What is the antiderivative of cosine? Sine. And this antiderivative is sine because if I were to take the derivative of sine, that gives me cosine. And it's really important that you write plus c at the end to remind yourself that a constant gets included with the antiderivative. It might not seem like that's important. Like you might like roll your eyes and think, yeah, that's kind of silly though. But this becomes really particularly important whenever you take a differential equations class. So if you're going to become an engineer, I know several of you in this room are going to become an engineer. You take Calculus 1, you take Calculus 2, you take Calculus 3, and then you take differential equations. And in differential equations, this is the most important thing in the entire world. That's like what the entire class is about. So we try not to forget to add plus c at the end to remind ourselves that a little constant term gets included with the antiderivative, because if I take the derivative of a constant, it's 0. So don't forget plus c. I will take off points on a test if you don't write plus c. It's offensive.
You said the d of x at the end just tells you that it's done. Like,
yeah, it tells you what variable you're taking the antiderivative with respect to, if that makes sense. Like, you know how already this semester we've done problems where sometimes we're like, have something like this, and we take the derivative with respect to time. Well, that would be different than if I took the derivative with respect to r, right? Those are different situations. And so whenever I say we're taking the antiderivative with respect to x, that tells me what derivative am I taking the antiderivative with respect to, because you would get a different answer if you were taking an antiderivative with respect to a different variable. Okay. What's the antiderivative of sine? Negative cosine. Yep. What's the antiderivative of secant squared? Tangent. Very good. What's the antiderivative of e to the x? E to the x plus c. I'm not going to take off all the points if you don't write plus c, but if you don't write plus c, I'll take off 1 point for every plus c that is missing from your test. It's that important. Memorize all the antiderivatives of common functions. So just like we did on day 1 of this class, like I would like you to make note cards, and the way your note cards should look is something like this. The front of your note card should say antiderivative of, I don't know, I'm trying to, my mind's going blank. We'll say antiderivative of cosine. You're going to do this for all of your antiderivatives. And then the back of your note card is going to say sine plus c. And you make a deck of note cards where you've got like 15 note cards for your 15 common antiderivatives you're supposed to memorize. And then you can practice whenever you want. Whenever you're stuck in traffic, you're waiting on the train, waiting in the drive-thru. All great opportunities to pull out your note cards and practice. So in this way, you can memorize your antiderivatives of common functions. The other thing here is like in your stuff you must memorize, I've got a page for antiderivatives of common functions. Pull that up really quick. Hopefully everybody kept this. But there's a page near the end of antiderivatives of common functions. And so these are all things that I would like you to know so that when you come across one of these common functions, you can quickly say what the antiderivative is. But the other thing, the flip side of this coin, is that not only do I want you to have the antiderivatives memorized, but I would also like you to be able to think about this, where you've already memorized all of these derivatives of common functions. So what I would like you to be able to do is to be able to spot one of these derivatives in the wild, kind of like we just did with the secant squared. When I asked you what the antiderivative of secant squared was, a lot of people thought tangent, because we're just moving in the opposite direction. So also, I should be able to ask you any questions about the derivatives on this page, and you should be able to tell me the antiderivative, you know, moving from the right side of the equation to the left side of the equation, in other words. So keep that in mind too. New vocabulary word is the word integral. This is what an integral is. An integral is the difference between an antiderivative evaluated at some upper bound minus an antiderivative evaluated at some lower bound. So we call this lowercase a the lower bound because it appears at the bottom end of the little squiggle. The b is called the upper bound because it shows up at the upper end of the tall squiggle. And so what you're going to do to evaluate an integral when you see an integral is you're going to say, all right, take the antiderivative of the stuff on the inside. The stuff on the inside is sometimes called the integrand. And so I take the antiderivative of this, and then I evaluate that at the upper bound, and I evaluate that at the lower bound, and I subtract. So I can find the difference between those. You'll see what I mean here. Let's do this little example. What's the antiderivative of x squared? 2. No. You just found the derivative of x squared. What's the antiderivative of x squared?
X third.
There you go. 1/3 x cubed. And then this is what I like to do for the intermediate step. I like to write big square brackets around the whole thing. When I say that, I like to write big square brackets around the antiderivative. And then the common thing to do is to write the lower bound as like a subscript on the bottom right corner and write the upper bound as a subscript on the top right corner. And then we're going to plug in what this looks like if I set x equal to 5. And so I write 1/3 5 to the third power in parentheses. And then I'm going to plug in what it looks like if I plug in x equals 2, which is 1/3 2 to the third power. And then, well, 5 to the third power is 125 minus 2 to the third power. And 125 minus 8 is 117 divided by 3. And 117 is divisible by 3. That would be 39. now you know how to integrate.
So on these ones, do we need to like have like a plus CL?
Oh, good question. Really good question, Carter. Thank you. So what would it look like if I added a little plus C? And I don't have like this nailed down. The C could be anything. It could be pi, it could be -7, it could be whatever. So the only rule here is that it has to stay the same. It has to be the same number, whatever I choose. And so then whenever I plug in x equals 5, it would be 1/3 5 cubed plus C. And then I would have, when I plug in 2, 1/3 2 cubed plus C. The reason why, when I evaluate an integral, I don't have to remember the plus C is because they're going to cancel each other out. Every time I do an integral, then the plus C from the upper bound is going to subtract away the plus C from the lower bound, and they're going to cancel each other out, and you just don't have that at the end. Yeah, that's a great question. I'm glad you asked. But yeah, when we do antiderivatives, we have to write plus C. When we do integrals, well, you don't have to. You can forget about it because it will cancel out. All right, here's another integral. So suppose I want to integrate secant squared of x from 0 to pi over 4. I'm going to write my square brackets. I'm going to write the lower bound here and the upper bound here. What goes inside the square brackets is the antiderivative of secant squared, which is tangent. So what is tangent of pi over 4? Tangent of pi over 4 is 1. What's tangent of 0? So that integral is 1. All right, so we draw big square brackets again. I put my lower bound here, my upper bound here. What is the antiderivative of 1 divided by x? Natural log of x. And then I'm going to plug in natural log of 10 from my upper bound. And then I subtract. What is natural log of 1? Yep. Any logarithm of 1 is 0. And so that's just going to be the natural log of 10. And just got to type in your calculator, I guess, to get natural log of 10. It's 2.303. So far, so good? So we talked about this at the beginning of the semester, but if you have a derivative has the properties of additivity and homogeneity. That means if I'm adding two things and I take the derivative, I can just take the derivative of each term separately. Super easy. Same thing. If I have a constant factor, like a constant multiplier in my derivative, like I want to take the derivative of 3x squared. Well, then the 3 just hangs out, right? You take the derivative of x squared, it's 2x, and then you multiply by 3, so it's 6x. That's what we call homogeneity. And I just want to point out that antiderivatives and integrals have the same properties. They both have additivity, they both have homogeneity. So if I'm adding two things on the inside of an antiderivative or adding two things on the inside of an integral, I can just take the antiderivative separately. I can just take the integral separately. It's fine. That's additivity. The other thing is, if I have a constant number in the integrand, if I have a constant factor on the inside of an antiderivative, I can just take it outside of the antiderivative if I want to. That way it's less cluttered. But that's called homogeneity, and that also works just fine. So where I see the integral from -1 to 1 of 2e to the x dx, I can just take the 2 out. That is integral homogeneity happening, right? It's totally fine if I take constant factors outside of the integral. Okay, what is the antiderivative of e to the x? E to the x. And so I plug in 1 and I plug in -1, I get e to the 1 power minus e to the -1 power and I get like 2.350, but then I multiply by that 2 that I took out of the problem from the beginning, and I get 4.701. Okay, next one. If I have the antiderivative, or sorry, the integral from 1 to 3 of x squared plus x cubed with respect to x, this is the same thing as taking the integral from 1 to 3 of x squared with respect to x plus the integral from 1 to 3 of x cubed with respect to x. This is what we call additivity. I can just take the antiderivative and the integral of both separately if I want to. Now, really, there's no reason in practice why you would want to do this versus, just writing it together as one big blob. There's not one way that's better than the other, but in theory, it becomes important.
So if we were to split it up, we don't really need to do that. We could just write it in one block, like on a test.
Yeah, it doesn't matter to me how you do it on a test. As long as you get the right answer, that's fine. So the antiderivative of x squared is 1/3 x cubed. And the antiderivative of x cubed is 1/4 x to the 4th. And so then we can plug in the 3 and get 9, plus plug in the 3 and we get 3 to the 4th power, which is 81 fourths, minus, now we plug in the 1s, and I'm sure you know how to work that out. Right? Find a common denominator, add and subtract your fractions, you can eventually get to the answer, but move it on to save time. Next, we're looking for the integral from -pi/6 to 0 of secant x times tangent x minus 2 with respect to x. And I think the point of me writing this is just to say that really, you can take the antiderivatives separately. between secant x and tangent x. Sorry, secant, tangent, and the 2. You don't have to rewrite it like this. That's not a requirement, and it's honestly just kind of a waste of a step, right? Like, why would you want to rewrite it like this? But I just want to point this out, that this is the idea behind integral additivity, is that I can separate an integral if I want to at a plus sign or a minus sign. It's a nice fact to know and be aware of. I don't think for this problem I would actually do that. Really, I would probably just keep it lumped together, but I would at least know in the back of my head that I can take those antiderivatives separately. So like, what's the antiderivative of secant times tangent? Secant. And what's the antiderivative of negative 2? Yeah, negative 2x. So at least I used that knowledge of like antiderivative additivity to take the antiderivative separately, and you're allowed to do that. And then the lower bound is negative pi over 6. The upper bound is 0. Secant of 0, I'll have to think about that for a moment, minus 2 times 0 minus secant of negative pi over 6 minus negative is going to be plus 2 divided by 6 is 1/3, so pi over 3. Okay, what is secant of 0? Well, secant is the reciprocal of cosine. What is cosine of 0? Yeah, cosine of 0 is 1. So secant of 0 is also 1. Minus 2 times 0, well, that's minus 0. What is secant of negative pi over 6? Well, that would be 1 divided by cosine of negative pi over 6. Cosine of negative pi over 6 is the same thing as cosine of positive pi over 6, because cosine is an even function, so it doesn't matter for an even function like cosine whether the argument's positive or negative. But still, I have to think about my unit circle and think about pi over 6. And cosine is the adjacent side over the hypotenuse. And this is a special right triangle. It's, do you remember the number? There you go. Very good. Square root 3 over 2. Lastly, I subtract pi over 3. Because I got to distribute that minus sign. So it's 1 minus square root 3 over 2 minus pi over 3. So at this point, the question you should be asking yourself is like, why do I care about integrals? That sounds so weird. Why do I take the antiderivative of a function? Why do I evaluate it at 2 different points? Why do I subtract them? Why does anybody care? A lot of people care about integrals, and we'll do some application problems here in a few days. But one geometric reason you might care is because an integral is the signed area in the xy plane between the curve that y equal the integrand and the x-axis between the lower bound and the upper bound. And whenever I say signed area, I mean that like in my xy plane, I've got the x-axis running through the middle, right? If anything is an area above the x-axis, it counts as positive area. And if you have any area below the x-axis, it's going to count as negative area. And at the end, when I take this integral, the integral is not going to tell me the total area. It's going to tell me like the net area. It's going to do positives minus negatives, which is a weird thing that you have to deal with, but that's how the math works. So I'll show you how you do this in geometry. For each of the following curves, like this curve y equals x squared minus 4, calculate the total area enclosed between the curve and the x-axis over the interval from a to b. So when you see a curve in some lower bound, upper bound on x, this is how we set up the integral. My integrand is my curve function here. What goes inside the box is my antiderivative. So what's the antiderivative of x squared? 1/3 x cubed. And then what is the antiderivative of negative 4?
0.
Negative 4.
Oh.
Yeah.
Oh, yeah.
The derivative of 4 is 0. The antiderivative is negative 4x. Very good. So now I have to evaluate this whole thing at the upper bound where it's 2, and it's going to be 1/3 times 8 minus 8. And then minus the whole thing evaluated at the lower bound, which is going to be negative 1/3 times 8 plus 8 So when we go to distribute the minus sign in the second part and then add all of this stuff together, it's going to be like 2 times 1/3 times 8. I've got to subtract 8 right here and subtract 8 right there, so it's going to be like minus 16. So like 1/3 of 16 minus 16 is like minus 2/3 of 16, or in other words, negative 32/3. That's my integral, is negative 32/3. Let's look at a picture of what we're doing right here. Let's check Desmos out for x squared minus 4. So x squared minus 4, that's my integrand. And what we said is that like we want the area between this curve and the x-axis from negative 2 to positive 2. So I could say x squared minus 4 less than y less than 0, but only for negative 2 to positive 2. So what we just calculated when we said negative 32 divided by 3 is this blue shaded area. It's the area that's enclosed between the curve, y equals x squared minus 4, and the x-axis. The reason we got a negative number for my integral is because this entire area was below the x-axis. And like I said, integrals will tell us about the signed area. So any area that's above the axis is going to count as positive, and the area that's below the axis is going to count as negative. So we ended up getting a negative answer because all of this is sitting below the axis. Now negative 32/3 is something a little bit shy of 11. Right? Yeah. This doesn't look like 11 though, does it? I mean, maybe I'm crazy, but I just feel like that's a lot less than 11. Did I make a mistake anywhere? Did I do my math wrong? Because each one of these blocks is 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, maybe that's 11. Desmos can also check your answer for integrals. Do you want to see how to check your answer? We're going to name my curve f of x, and then I can tell Desmos int, it'll bring up the squiggle if you type in int, and then lower bound -2, upper bound 2 of f of x dx. Okay, so it is right. We got the right answer. Desmos will tell you it's a little bit shy of -11.
So whenever you check it, is it just whatever box like it touches, or does it have to be like the full box to count it? Like the area,
Yeah.
or like for the 11, is it like whatever box it touches, it just counts as 1?
No. No, definitely not. Because like it's touching a lot of boxes, right? Like how many boxes is it just touching? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But really what I'm doing in my head is I'm like, well, there's 6 full boxes. And this kind of look like they could add together to be 1. This and this could be another one. So now I'm at 8. Maybe this one and this one add together to be 9, and this one and this one add together to be 10. So in my head, I was like, I know this is around 10. I don't know if it was around 11, but that's what we can double check. But no, to answer your question, the integral does the exact area for curves. It doesn't chunk it into blocks or anything like that. That's just what I'm trying to do in my head to do a sanity check on the answer. But no, this is cool, I think, because previously in geometry class, you learned how to take the area of squares and rectangles and triangles and circles, but you were kind of limited in terms of the number of different shapes you could calculate areas for. This is the first time in your life when you can calculate any area that you want. You know, you just describe the area with a function and you can do it. Let me scroll back up because we already took several integrals actually. So like, what the heck is the integral 39 about? Well, that would be the integral from 2 to 5 of x squared. So here is the x squared function. And here is what it looks like to have the area between 2 and 5. So it's a little bit of a weird shape. But this purple area, the purple shaded area, has an area of 39. Right? That's geometrically what we're doing, is we make a lower bound vertical line at x equals 2, an upper bound vertical line at x equals 5, and all of the area shaded between the curve and the line counts towards the integral. And we got positive 39 this time because all of the area was above the x-axis. What about the integral of secant squared from 0 to pi over 4? So that is the area we're talking about, because the red curve is the secant squared curve, and my bounds were 0 to pi over 4, so the purple shaded area is the value of this integral. So that purple shaded area has an area of 1. Yeah?
If we have a lower bound that's negative and the upper bound is positive, like will the area below the x-axis, like that would be negative, but then we have a positive, so we're like...
They'll cancel each other out.
Actually the total area?
Yep, that's a really good question. Yeah. Yeah, so let's talk about that too. My next two examples should hopefully address this for you, because it is a really good question. We've got the function cosine of x, and I want to know what's the total area between the cosine curve and my x-axis on the interval from negative pi over 2 to positive pi over 2. So I'm going to set up my integral. Okay, what's the antiderivative of cosine? Sine. So I'm going to calculate what is sine of pi over 2. One. Now what is sine of negative pi over 2? Negative 1. So the integral of cosine from negative pi over 2 to positive pi over 2 is 2. And that means, as long as my curve didn't cross the axis, that the area under the curve, or the area between the curve and the x-axis, is 2. Let's take a look at what that would look like. Because here's cosine in red, and here is from negative pi over 2 to positive pi over 2. So the purple shaded area has an area of 2. Okay. What about this? Same thing, but I want this time the total area between the cosine curve and the x-axis over this interval from negative pi over 2 up to 3 pi over 2. So same thing, the antiderivative is sine. What is sine of 3 pi over 2? Negative 1. What is sine of negative pi over 2? We just did this one. It's negative 1. So what's negative 1 minus negative 1? 0. So the reason my integral gave me a 0 is because I'm looking for the area between the curve and the x-axis from negative pi over 2 to 3 pi over 2. So let me shade in what that looks like on Desmos. Okay. So this is my lower bound, negative pi over 2. This is my upper bound, 3 pi over 2. And with the whole idea of the cosine function, this is just like a repeating thing. It's symmetric in so many ways. The purple shaded area is exactly the same size as this black shaded area. But remember, areas above the x-axis count as positive. Areas below the x-axis will count as negative in my integral. And since these are exactly the same size, they exactly cancel each other out, and I get a 0. So the way to do this would then just be like, well, the integral is not going to directly tell me the total area, but if I know that the area is just going to be this number times 2, because it's the same shape, right, above the curve, below the curve, then the total area between the curve and the x-axis must be 2 times 2, right? But Avery's 100% correct. Since they are signed areas, when I add them together, sometimes they will cancel each other out. Let's do another one. For the following curve, and this is, to me, is the trickiest kind of question because there's a lot of investigating we have to do for this one. But it says, for the following curve, calculate the total area enclosed between the curve and the x-axis for the given interval from -2 to +2. So if I want the total area, I can tell you right now that this is going to give me 0 as an integral, and that is not the correct answer. There is more than 0 area between the curve and the x-axis. So that's not going to work for us. We've got to be a little bit smarter about how we do something like this. Instead, I think what you should do is find the places where this curve passes through the x-axis. In other words, we're going to find the x-intercepts of this curve by setting x cubed minus x equal to 0. One of them happens at x equals 0. How do I factor x squared minus 1? So I have x-intercepts, or places where my curve passes through the x-axis, at -1, 0, and 1. If you remember how to graph polynomials back in your pre-cal or college algebra days, this graph is going to look like this. It's x cubed and it has a positive coefficient, so it's going to go up on the right, and then it's going to go through the axis here, up through the origin here, and then boom. And here's 1, here's -1, and let's say this is -2 and this is +2. But if I took the integral from -2 to +2 of this curve, the problem is that like this counts as negative area and this counts as negative area. And the negative area on the far left is going to cancel out with this positive area on the right side. And this negative area, and that little value is going to cancel out with this positive area in this little hill. You see how those are going to be exactly the same shape, exactly the same size, but half are negative and half are positive, so they're just going to cancel each other out. So the way to do this, then, is you could say, well, maybe what I do is I take the integral from -2 to -1, which is going to give me this part in red. But I know that's going to give me a negative number. So I'm going to put a negative sign in front of it to make it positive. And then I'll take the integral from -1 to 0, and that's going to give me a positive number because it's above the x-axis. And so I'm going to leave that as positive. And then I'm going to take the integral from 0 to 1, but that's going to give me a negative number because it's area below the x-axis. So I'm going to make that a minus in order to make the negative into a positive. And then lastly, I'm going to take the integral from 1 to 2, because that's going to be positive area above the axis. So, antiderivatives now, right? We've got to do that. We're going to take the antiderivative of x cubed, which is
1 over x, no, 1 over 4x to the 4th.
Very good. 1 over 4x to the 4th. And then the antiderivative of minus x will be minus 1/2 x squared, yep. Lower bound -2, upper bound -1. Plus the same thing with lower bound -1, upper bound 0, minus the same thing with lower bound 0, upper bound 1, plus the same thing with lower bound 1, upper bound 2. Whenever I look at this, I see so many different symmetries and ways to simplify this that I don't really even know where to begin. For one thing, what do I know about x squared and x to the 4th power? Right? If I take a negative number and I plug it into x squared, negative numbers squared are still positive. What if I take a negative number and I plug it into x to the 4th power? Well, a negative number raised to the 4th power is still positive. And so it turns out it doesn't matter whether I'm plugging in 1 or -1, and it doesn't matter whether I plug in 2 or -2, I get the same answer. Okay? So since I've only got even powers of x, whether it's positive or negative doesn't really matter. So here's another question for you to think about for a moment. If I have a minus sign in front of this whole thing, lower bound A, upper bound B, wouldn't this be the same thing as this? If I switch the lower bound, upper bound stuff, in other words, I make the upper bound into the make the lower bound into the upper bound and the upper bound into the lower bound. All that's going to do is it's going to reverse the order in which I'm subtracting the antiderivatives. But reversing the order of subtraction is the same thing as multiplying by a -1. Okay? Does everybody feel good about that? Because if you feel comfortable with this idea that switching the upper and lower bound is just multiplying by -1, then we can simplify this a lot. Because if I say, it doesn't really matter if this is a 1 or a -1, I get the same answer because they're squared, well then forget the negatives, right? I'll just erase all of the minus signs. And then I think, well, if this has a minus sign in front of it, I could just switch the upper and lower bound instead, switch the 2 with the 1, and I can get rid of that minus. And what about here where there's a minus sign? I can make that a positive if I switch the upper and lower bounds. And then, hey, look at that. This becomes easier now because I just have this antiderivative show up here with bounds 2 and 1, and it shows up over here with bounds 2 and 1. So twice that, plus the same thing, lower bound 1, upper bound 0. Twice, because it shows up twice. Okay, now we can, start to evaluate this. I've got 2 times this one first. I'll plug in the 2 and get 2 to the 4th power divided by 4, which is really 16 divided by 4, which is 4. And then minus 1/2 2 squared, which is half of 4, that's minus 2. Then the lower bound, where I plug in 1. Plus, and I've already factored out this 2 and put it on the outside of the parentheses. What do I get if I plug in the 0? Minus, what do I get if I plug in the 1? Well, I actually already plugged in the 1 before. That was 1/4 minus half. 4 minus 2 is 2. 1/4 minus a half would be negative 1/4. Times a negative makes it positive 1/4. Plus 0 plus another positive 1/4. And that is 2 times 2 1/2, which is 5. Nice. So the total area in between this curve and the x-axis is 5. Let's put it in Desmos and see what it looks like. The lower bound was negative 2. Upper bound was positive 2. I'm going to shade the negatives so that they're red and the positives so that they're green, and then they're blue. Nice color coding. All right, so this is again the picture of what we're trying to find. What I would really like is to have all 4 of these areas added up. But if I ask Desmos to just integrate between negative 2 and positive 2 for me, it gives me an integral of 0 because the green areas cancel out the red areas exactly. So the annoying part of this is saying, okay, I first need negative the integral from negative 2 to negative 1 f of x dx, plus the integral from negative 1 to 0 f of x dx, minus the integral from 0 to 1 f of x dx, plus the integral from 1 to 2 f of x dx, and that's 5 to check our answer. By the way, for checking my answer on Desmos, what's another super duper easy fix?
Can you just find the positive?
I could just put absolute value signs around the f of x to make this a heck of a lot easier for me to do in Desmos, right? Because this is forcing the function to be positive, and it's calculating that area instead. And so that's another way you can do the total area thing. Absolute values don't help you whenever you are taking the integral, but it helps Desmos. Yeah.
When we are taking the integral, We just found the green, area of the green, and then times it by 2.
Yeah, you're right. If you know that your function is an odd function so that you have this symmetry, you remember odd functions from college algebra, if you know that you have this particular kind of symmetry, then yeah, you can absolutely just do the green areas times 2. Yeah, not all functions are like that. Like, what if I had instead given you this function, right? Now, you've got some green and some red, but you don't, there's no canceling them out or anything like that. You've still got to find the intersection and make 2 integrals separately. Or even worse, I mean, that would be fine as a problem. That wouldn't be too difficult, but even worse, maybe situations arrive in real life where you've got something like this, where, I mean, that's just gross. You have to take 4 integrals, and there's no way to simplify this because the areas don't cancel each other out easily. So keep that in mind. As you go and do your homework, the questions that say, like, calculate the total area, try to think to yourself, is the area I'm finding above the curve, or above the x-axis, I mean? Is it below the x-axis, or is it a mixture of above and below, where I need to actually break it down into smaller problems? But yeah, now you're no longer limited to just squares and circles. Any shape you can imagine and put into function form, now you can find the area.